For centuries, humanity has looked up at the night sky and wondered about the Milky Way, the vast river of stars that arcs across the darkness. This luminous band, visible on clear nights, far from city lights, is our home galaxy, a cosmic island containing hundreds of billions of stars, countless planets, nebulae, star clusters, and at its heart, a supermassive black hole. We've long believed we understood the Milky Way's basic dimensions, its size, its mass, and its place among the galaxies of the universe. But recent measurements, using cutting-edge technology and innovative techniques, have revealed something unexpected. Our galaxy is smaller than we thought. This discovery is not just a matter of updating numbers in a textbook. It has profound implications for our understanding of galactic structure, cosmic history, and our place in the universe. The new measurements suggest that the Milky Way's disk, the flat, spiral structure where most of the galaxy's stars reside, extends less far than previous estimates indicated. The total mass of the galaxy appears to be lower, and the distribution of dark matter in the galactic halo may be different from what we assumed. These findings come from multiple independent research teams using different methods, from tracking the motion of stars at the galaxy's edge to analysing the orbits of satellite galaxies and globular clusters. The convergence of these results suggests we're not dealing with measurement errors or statistical flukes, but with a genuine revision of our understanding of the Milky Way's true scale. Why does this matter? Understanding the size and structure of our galaxy is fundamental to almost every aspect of astronomy. The Milky Way serves as a laboratory for studying galactic physics, star formation, chemical evolution, and the nature of dark matter. It's also our cosmic context, the framework within which we understand our solar system's place and motion. If we've overestimated the galaxy's size, it means we need to recalibrate our understanding of how galaxies form and evolve, how stars are distributed in galactic disks, and how dark matter structures galaxies. Before we explore the details of these new measurements and what they mean, drop it in the comments below where in the world you're watching from and what time it is there. Now, settle in as we journey through the Milky Way and discover what these groundbreaking findings tell us about our cosmic home. How Gaia satellite mapped 1 billion stars to find the truth. The hero of this story is a spacecraft that most people have never heard of, but which has revolutionized our understanding of the Milky Way more than any other mission in recent decades. The Gaia satellite, launched by the European Space Agency in December 2013, has been quietly orbiting the Sun at a distance of about 1.5 million kilometers from Earth, systematically mapping the positions, distances, and motions of over 1 billion stars in our galaxy. That's right, 1 billion stars, each measured with extraordinary precision, creating the most detailed three-dimensional map of the Milky Way ever constructed. Gaia's mission is deceptively simple in concept, but extraordinarily complex in execution. The spacecraft continuously scans the sky, measuring the exact positions of stars with an accuracy that would be equivalent to measuring the diameter of a human hair from a distance of 1,000 kilometers away. But Gaia doesn't just measure where stars are, it measures how they move. By tracking the same stars over months and years, Gaia can determine their velocities through space, revealing the dynamic nature of our galaxy and allowing astronomers to trace the orbits of stars backward and forward in time. The breakthrough that led to the new measurement of the Milky Way's size came from Gaia's third data release in 2020, known as Gaia DR3. This release contained unprecedented measurements of the motions of stars in the outer regions of the galaxy, the faint, distant stars that mark the boundary between the Milky Way and intergalactic space. These are exactly the stars astronomers needed to observe to determine where our galaxy truly ends, and Gaia delivered data of unprecedented quality. What Gaia revealed was shocking. By analysing the velocities and distances of stars at various radii from the galactic centre, astronomers could construct a new rotation curve for the Milky Way, a graph showing how fast stars orbit at different distances. This rotation curve is critical because it's directly related to the distribution of mass in the galaxy, including the invisible dark matter that makes up most of the galaxy's mass. And what the new rotation curve showed was unmistakable. The Milky Way's mass drops off more steeply at large radii than previous models had predicted. In other words, the galaxy is smaller and less massive than we thought. The precision of Gaia's measurements is what makes this discovery so definitive. Previous estimates of the Milky Way's size relied on indirect methods and assumptions that introduced significant uncertainties. Gaia, by contrast, provides direct measurements of stellar positions and velocities with errors of just a few % or less. When hundreds of millions of such measurements are combined, the result is a picture of the galaxy's structure and mass distribution that is far more accurate than anything we had before. For the first time, we can confidently say we know how big our galaxy really is, and the answer is smaller than we expected. The 2020 bombshell. We're 10–15% smaller than we thought. The recent finding that the Milky Way is smaller than we thought comes from several independent lines of evidence, each using different methods and datasets. This convergence of results from multiple approaches is what makes the discovery credible and significant. Let's examine the key techniques that have led to this revision. One crucial method involves measuring the motions of stars at the edge of the Milky Way's disk. By determining how fast these stars are moving and in what direction, astronomers can infer the mass distribution of the galaxy and the extent of its gravitational influence. If stars at a certain distance are moving more slowly than expected, it suggests they are at or beyond the edge of the galaxy's main disk, where the gravitational pull is weaker. Recent studies using data from the Gaia satellite have identified stars that appear to mark the outer boundary of the disk, and this boundary is closer to the galactic center than previous estimates suggested. Gaia's contribution to this discovery cannot be overstated. The mission has measured the precise positions, distances, and motions of over 1.8 billion stars with unprecedented accuracy. By analysing the three-dimensional distribution of these stars and their velocities, astronomers can map the structure of the galactic disk in exquisite detail. Studies published in the early 2022 using Gaia data have consistently found that the stellar density in the disk drops off more sharply than expected, suggesting a more compact structure. The effective radius of the disk, defined as the radius containing half the galaxy's light or mass, appears to be about 10–15% smaller than previous estimates, placing it around 45,000 to 50,000 light-years rather than 50,000 to 60,000 light-years. Another line of evidence comes from studying the Milky Way's satellite galaxies, small galaxies that orbit the Milky Way, like moons orbit a planet. The motions of these satellites are governed by the Milky Way's gravitational pull, so by measuring their orbits, astronomers can infer the total mass of the Milky Way, including its dark matter halo. Recent measurements of the velocities and distances of satellites, like the Large and Small Magellanic Clouds, along with more distant dwarf galaxies, have suggested that the Milky Way's total mass is lower than previously thought. Estimates now converge on a total mass of about 700 billion to 1 trillion solar masses, compared to earlier estimates of 1 to 1.5 trillion solar masses. This reduction in estimated mass has important implications. If the Milky Way is less massive, its gravitational influence extends less far, and the outer regions of the disk and halo would be correspondingly smaller. The dark matter halo, which dominates the galaxy's mass and extends well beyond the visible stars, appears to be less extensive than assumed. This doesn't mean dark matter is less important. It's still the majority of the galaxy's mass, but the overall structure is more compact. A third approach involves analyzing the rotation curve of the Milky Way, the relationship between orbital speed and distance from the galactic center. In a classic disk galaxy, stars closer to the center orbit faster, and those farther out orbit more slowly. However, observations of the Milky Way and other galaxies show that rotation speeds remain relatively constant, far from the center, a phenomenon attributed to the presence of dark matter. By measuring the rotation curve with high precision and comparing it to models, astronomers can constrain the distribution of mass throughout the galaxy. Recent studies using data from large spectroscopic surveys, which measure the velocities of stars and gas clouds, have found that the rotation curve flattens at a smaller radius than expected, again suggesting a more compact mass distribution. Radio observations of hydrogen gas, which extends farther from the galactic center than most stars, also contribute to this picture. The 21 centimeter line emission from neutral hydrogen allows astronomers to trace the outer disk and measure its extent. Recent surveys have mapped the hydrogen distribution with high sensitivity, and they find that the gas density drops off more steeply than older observations suggested. This is consistent with a smaller overall disk size. Finally, simulations of galaxy formation and evolution provide a theoretical framework for interpreting the observations. Modern cosmological simulations, which model the growth of structure in the universe, from the Big Bang to the present, predict how galaxies of different masses and environments should form and evolve. When these simulations are calibrated to match the observed properties of the Milky Way, they tend to favor a galaxy that is somewhat less massive and less extended than the traditional picture. The simulations also suggest that our earlier estimates may have been biased by assumptions about the distribution of stars and dark matter that were not quite correct. Taken together, these multiple lines of evidence paint a consistent picture of a Milky Way that is more compact than we thought. The disk extends less far, the total mass is lower, and the dark matter halo is less extensive. The differences are not enormous, typically on the order of 10 to 20%, but they are significant enough to require a revision of our understanding, tracking stars at the edge, where the Milky Way stops. One of the most profound challenges in galactic astronomy is determining where a galaxy ends. Unlike a planet with a solid surface or a star with a well-defined photosphere, galaxies don't have sharp boundaries. They fade gradually into the surrounding intergalactic space, making it extremely difficult to define precisely where the galaxy stops and the void begins. For the Milky Way, this problem is especially acute because we're observing from inside the galaxy itself, embedded in its disk, surrounded by stars in all directions. To find the edge of the Milky Way, astronomers look for specific types of stars that serve as tracers of the galaxy's outer regions. These include RR Lyrae variable stars, old pulsating stars that are bright enough to be detected at great distances, and blue horizontal branch stars, which are also relatively luminous and easy to identify. By measuring the distances and velocities of these tracer stars, astronomers can map out the extent of the galaxy's stellar halo, the roughly spherical distribution of old stars that surrounds the galactic disk. Gaia's observations of these distant stars revealed something surprising. The stellar halo doesn't extend as far as previous models had suggested. Most earlier estimates, based on limited observations and theoretical models, had placed the edge of the Milky Way's halo at about 200,000 to 250,000 light-years from the galactic center. But Gaia's data showed that the density of stars drops off much more rapidly, with the halo effectively ending at around 130,000 to 150,000 light-years, depending on how you define ending. This discovery has profound implications for understanding the Milky Way's mass. The halo contains not just stars, but also a significant amount of dark matter, the mysterious, invisible substance that makes up most of the mass in galaxies. By measuring where the stellar halo ends, astronomers can constrain where the dark matter halo ends as well, at least the densest part of it. And if the dark matter halo is smaller than we thought, then the total mass of the galaxy must be smaller too. But defining the edge of the galaxy is still not entirely straightforward. Even beyond the main stellar halo, there are streams of stars that have been tidally stripped from satellite galaxies orbiting the Milky Way. These streams can extend hundreds of thousands of light-years into space, far beyond the main body of the galaxy. Are they part of the Milky Way or separate structures? The answer depends on your definition, but for practical purposes, astronomers now define the Milky Way's edge as the point where the density of stars belonging to the main halo drops below a certain threshold, typically where the stellar density becomes comparable to the density of stars in the intergalactic space of the local group. The discovery that we can now accurately track individual stars out to these enormous distances is itself a testament to the power of modern astronomy. Just a few decades ago, astronomers struggled to measure distances to stars more than a few thousand light-years away. Today, thanks to missions like Gaia, we can map the entire structure of our galaxy in 3 dimensions with exquisite detail. We've gone from wondering how big the Milky Way is to knowing precisely where it ends, a remarkable achievement that has fundamentally changed our understanding of our cosmic home. Satellite galaxies reveal our true mass. The Milky Way does not exist in isolation. It is surrounded by a retinue of satellite galaxies, smaller galaxies that orbit it much like moons orbit a planet. These satellites provide valuable information about the Milky Way's mass, its gravitational influence, and its history of interactions and mergers. The discovery that the Milky Way is less massive affects our understanding of these satellites and their relationship to the host galaxy. The largest and most prominent satellites are the Large Magellanic Cloud and the Small Magellanic Cloud, or LMC and SMC. These are irregular dwarf galaxies, visible to the naked eye from the southern hemisphere, appearing as faint, cloudy patches. The LMC is about 160,000 light-years from the Milky Way and has a mass of roughly 10 billion solar masses, making it a substantial satellite. The SMC is about 200,000 light-years away and is less massive. Both clouds are undergoing active star formation and contain significant amounts of gas and dust. Recent observations have shown that the LMC and SMC are likely on their first passage around the Milky Way rather than being long-term satellites. Their high velocities and large distances suggest they are just now being captured by the Milky Way's gravity. This has important implications, as the gravitational influence of the LMC can affect the Milky Way's disk and halo, potentially causing distortions and triggering star formation. The LMC is massive enough to have its own satellite galaxies, and some of the other dwarf galaxies around the Milky Way may have originally been satellites of the LMC. Beyond the Magellanic Clouds, the Milky Way has dozens of known dwarf satellite galaxies, most of them dwarf spheroidals. These are faint, diffuse galaxies with little or no ongoing star formation, containing mostly old stars. Examples include Draco, Ursa Minor, Sculptor, and Fornax. These dwarfs are thought to be the remnants of once more active galaxies that have had their gas stripped away by the Milky Way's tidal forces and by ram pressure as they move through the hot corona. In recent years, many new ultra-faint dwarf galaxies have been discovered, some containing only a few thousand stars. These objects are extremely difficult to detect because they are so faint and sparse, but large area surveys like the Sloan Digital Sky Survey and the Dark Energy Survey have been successful in finding them. Ultra-faint dwarfs are important for testing models of galaxy formation on the smallest scales and for understanding the nature of dark matter, as they appear to have very high dark matter to stellar mass ratios. The orbits of satellite galaxies are governed by the Milky Way's gravitational potential, and by studying these orbits, astronomers can infer the total mass of the galaxy and the distribution of dark matter. If the Milky Way is less massive, the satellite's orbits are correspondingly affected, with implications for their long-term stability and for the timing of future interactions. Some satellites are on highly elliptical orbits that bring them deep into the Milky Way's halo, where they can be tidally disrupted, while others are on more circular orbits at greater distances. The Milky Way is also part of the Local Group, which includes the Andromeda Galaxy and about 50 other members. The Local Group is a gravitationally bound structure, and its members are slowly moving toward a common centre of mass. The dynamics of the Local Group depend on the masses of the Milky Way and Andromeda, and the revised estimate of the Milky Way's mass affects predictions for the future evolution of the group, including the timing and details of the Milky Way-Andromeda collision. The rotation curve mystery, spinning slower than expected. One of the most powerful tools astronomers have for measuring the mass of a galaxy is its rotation curve, a graph that shows how fast stars and gas orbit the galactic center as a function of their distance from that center. For a simple system like the solar system, where most of the mass is concentrated in the Sun, the rotation curve is easy to predict. Planets farther from the Sun orbit more slowly, following Kepler's laws. But galaxies are different. They're not dominated by a single central mass, but contain matter distributed throughout their volume, including vast amounts of invisible dark matter. For the Milky Way, constructing an accurate rotation curve has been a goal of galactic astronomy for decades. The challenge is that we need to measure the velocities of stars and gas clouds at a wide range of distances from the galactic center, from the innermost regions just a few thousand light years, from the center out to the edge of the galaxy 100,000 light years or more away. This requires observations across the entire sky and sophisticated techniques to disentangle the complex motions of stars in our rotating, spiral galaxy. Gaia's data allowed astronomers to construct the most accurate rotation curve of the Milky Way ever produced. By measuring the velocities of millions of stars at precisely known distances, Gaia revealed the detailed shape of the rotation curve with unprecedented precision. And what that curve showed was a surprise. In the outer regions of the galaxy, stars are orbiting more slowly than previous models had predicted. This slower rotation means there's less mass in those outer regions than astronomers had thought, providing direct evidence that the Milky Way is less massive overall. The rotation curve also reveals the distribution of dark matter in the galaxy. Dark matter doesn't emit light, so we can't see it directly, but we can detect its gravitational influence on the motions of stars and gas. The fact that stars in the outer Milky Way orbit more slowly than expected suggests that the dark matter halo is less extended and less massive than earlier estimates indicated. This has implications not just for our understanding of the Milky Way, but for our understanding of how galaxies form and evolve in general. What makes this discovery particularly significant is that it contradicts decades of assumptions based on less precise data. For years, astronomers thought the Milky Way's rotation curve remained roughly flat out to very large radii, similar to what's observed in many other spiral galaxies. This flat rotation curve was one of the key pieces of evidence for the existence of dark matter in the first place, showing that there must be invisible mass extending far beyond the visible disk. But Gaia's new measurements show that the Milky Way's rotation curve isn't perfectly flat. It drops off more steeply in the outer regions than we realized. This doesn't mean dark matter doesn't exist, far from it, but it does mean our models of how much dark matter the Milky Way contains need to be revised downward. The implications are still being worked out, but one thing is clear. Measuring how fast stars orbit the galaxy is one of the most direct ways to weigh the Milky Way. And thanks to Gaia, we now know that the galaxy is lighter than we thought. It's a humbling reminder that even basic facts about our own galaxy, things we thought we understood well, can be overturned by better observations. Science is a process of continuous refinement, and the Milky Way's rotation curve is a perfect example of how new data can force us to revise our understanding. Why we overestimated for decades. For decades, astronomers have been systematically overestimating the size and mass of the Milky Way, and understanding why reveals fundamental challenges in measuring our own galaxy and highlights how scientific knowledge progresses through the gradual correction of errors. The reasons for the overestimation are complex, involving a mix of observational limitations, theoretical assumptions, and the simple fact that measuring something from inside it is extraordinarily difficult. One major source of error was the limited data available for stars in the outer regions of the galaxy. These stars are faint, distant, and difficult to observe, so early estimates of the Milky Way's extent were based on small samples of stars whose distances were uncertain. Astronomers had to extrapolate from these limited observations to estimate the total size and mass of the galaxy, and those extrapolations often turned out to be too optimistic. It's like trying to estimate the size of a city by sampling a few buildings. If you happen to sample mostly large buildings, you'll overestimate the average size. Another factor was the influence of theoretical models. For much of the 20th century, astronomers believed that the Milky Way was roughly comparable in size to the Andromeda galaxy, which was easier to observe because we view it from outside. Estimates of Andromeda's size influenced estimates of the Milky Way's size through the assumption that two similar-looking spiral galaxies should have similar properties. But this assumption turned out to be wrong. Andromeda is significantly larger and more massive than the Milky Way, and using it as a template led to overestimates of our galaxy's size. A third issue was the challenge of measuring distances in the galaxy. Until very recently, measuring the distance to a star more than a few thousand light-years away was extremely difficult and prone to large errors. Techniques like spectroscopic parallax and standard candles like Cepheid variables provided rough estimates, but each method had its own systematic uncertainties. These uncertainties tended to compound, so that estimates of the distances to the most remote stars in the galaxy could be off by 20, 30, or even 50%. If you overestimate the distances to stars, you'll overestimate the size of the galaxy. Perhaps most importantly, astronomers lacked good measurements of the Milky Way's total mass. Estimating mass requires observing the motions of objects orbiting under the galaxy's gravity, such as satellite galaxies or stars in the outer halo. But for a long time, there weren't enough such objects with well-measured distances and velocities to provide a reliable estimate. Astronomers had to rely on theoretical models that made assumptions about the distribution of dark matter in the galaxy, and these models often predicted more dark matter and thus more total mass than actually exists. All of these factors combined to create a picture of the Milky Way that was, in retrospect, too grand. We thought we were a galaxy of perhaps 1.5 to 2 trillion solar masses, one of the giants of the local group, roughly comparable to Andromeda. The new measurements, based on Gaia's precise data, and improved distance estimates paint a more modest picture. A galaxy of about 1 to 1.2 trillion solar masses, significantly smaller than Andromeda and more middle of the road in the grand scheme of galaxies. This downward revision is a healthy reminder that science is always provisional. What we know today is simply our best current approximation of the truth, subject to revision as new data becomes available. The Milky Way hasn't shrunk, of course, it was always the size it is. But our knowledge of its size has changed, and that change is a victory for the scientific method. We're getting closer to the truth, and that's something to celebrate, even if the truth is smaller than we expected. The Shapley-Curtis debate. When we thought we were huge, the discovery that the Milky Way is smaller than we thought is not the first time astronomers have had to revise their understanding of our galaxy. The history of galactic astronomy is marked by major shifts in perspective, each driven by new observations and new techniques. Understanding this history helps us appreciate the current finding in context and reminds us that our knowledge of the universe is always provisional, subject to revision as we learn more. In the early 20th century, the dominant view was that the Milky Way was the entire universe. The Dutch astronomer Jacobus Kapteyn developed a model of the galaxy based on star counts, placing the Sun near the center of a disc-shaped system about 40,000 light-years in diameter. However, Kapteyn's model was limited by the effects of interstellar dust, which absorbs and scatters light, making distant stars appear fainter and less numerous. This led to an underestimate of the galaxy's true size. Harlow Shapley challenged this view in the 1,910 seconds by studying globular clusters, dense balls of old stars distributed in a halo around the galaxy. Shapley used Cepheid variable stars in the clusters to estimate their distances and found that they were arranged in a roughly spherical distribution centered on a point far from the Sun's position. He concluded that the galactic center was about 50,000 light-years away in the direction of the constellation Sagittarius, and that the Milky Way was much larger than Kapteyn's model suggested, about 300,000 light-years in diameter. Shapley's estimate of the size was too large, primarily because he overestimated the distances to the globular clusters, but he correctly identified the galactic center's direction and established that the Sun was not at the center of the galaxy. The realization that spiral nebulae were external galaxies, confirmed by Hubble in 1924, forced a rethinking of the Milky Way's structure and size. If Andromeda and other spirals were comparable to the Milky Way, they provided templates for understanding our own galaxy. By the mid-20th century, a more accurate picture had emerged. The Milky Way was a large spiral galaxy, with a disk about 100,000 light-years in diameter and a central bulge. The Sun was located about 25,000 to 30,000 light-years from the center, and the galaxy contained a few 100 billion stars. In the 1,970 seconds, the discovery of dark matter revolutionized galactic astronomy. Observations by Vera Rubin, Kent Ford, and others showed that stars and gas in the outer parts of spiral galaxies were moving faster than expected based on the visible mass. This flat rotation curve implied the presence of large amounts of unseen mass extending far beyond the visible disk. The realization that galaxies are dominated by dark matter led to a reinterpretation of their structure and dynamics. The Milky Way, like other galaxies, was understood to be embedded in a massive dark matter halo, with the visible stars and gas representing only a small fraction of the total mass. More recent revisions have come from improved measurements of stellar distances and motions. In the 1,990 seconds, the Hipparcos satellite measured the parallaxes of over 100,000 stars, leading to more accurate distance scales and a refinement of the galaxy's size and structure. The discovery of the Sagittarius dwarf elliptical galaxy in 1994 revealed that satellite galaxies could be hidden within the Milky Way's halo, disrupting and being absorbed over time. This finding changed our understanding of how the galaxy has grown through the accretion of smaller systems. The Gaia mission, launched in 2013, represents the latest revolution. With precise astrometry for over 1 billion stars, Gaia has revealed the detailed structure of the disk, the halo, and the streams left by disrupted satellites. It has also shown that the Milky Way's history is more complex than previously thought, with multiple merger events contributing to the build-up of the halo and bulge. The current finding that the galaxy is smaller is another step in this ongoing process of refinement, driven by ever-improving data. These historical revisions remind us that our picture of the Milky Way is not static, but evolves as new observations become available. Each generation of astronomers works with the best data and techniques of their time, but there is always room for improvement. The key is to remain open to the possibility that our current understanding might be incomplete or incorrect, and to be willing to revise our models when the evidence demands it. From 300,000 to 100,000 light-years, a history of shrinking. To appreciate the significance of this discovery, we need to understand how our conception of the Milky Way has evolved over time. For most of human history, the nature of the Milky Way was a mystery. Ancient Greek philosophers debated whether it was a terrestrial or celestial phenomenon. Aristotle believed it was atmospheric, a kind of exhalation from the Earth that glowed in the upper atmosphere. Others, like Democritus, proposed that it was composed of distant stars, too faint individually to be seen but collectively creating a luminous band. The question remained unresolved until 1610, when Galileo Galilei turned his newly invented telescope toward the Milky Way and discovered that it was indeed made of countless stars. This observation was revolutionary, suggesting that the universe was far larger and more complex than anyone had imagined. But even Galileo could not determine the Milky Way's true structure or our position within it. For the next 3 centuries, astronomers debated whether the Milky Way was the entire universe or just one island of stars among many. In the early 20th century, the great debate of 1920 between astronomers Harlow Shapley and Heber Curtis addressed the nature of spiral nebulae, cloudy objects visible through telescopes. Shapley argued that these nebulae were part of the Milky Way, making our galaxy enormous, while Curtis contended they were separate galaxies, making the Milky Way smaller but the universe vastly larger. The question was settled in 1924 when Edwin Hubble, using the 100-inch telescope at Mount Wilson Observatory, identified Cepheid variable stars in the Andromeda Nebula. By measuring the periods of these stars, Hubble calculated that Andromeda was far too distant to be part of the Milky Way. It was a separate galaxy, and the universe was suddenly understood to contain billions of such galaxies. This discovery established the basic framework for understanding the Milky Way as one galaxy among many. Over the following decades, astronomers worked to map the Milky Way's structure, determine its size, and understand its components. By the mid-23rd century, a picture had emerged of the Milky Way as a large spiral galaxy with a central bulge, a thin disk containing spiral arms, and a spherical halo of old stars and globular clusters. Estimates of the galaxy's diameter ranged from 100,000 to 120,000 light-years, with the Sun located about 25,000 to 28,000 light-years from the galactic center. These measurements were challenging because we observe the Milky Way from inside it, embedded in the disk. Dust in the galactic plane obscures our view in visible light, making it difficult to see the full extent of the galaxy or to determine its overall structure. Astronomers had to use indirect methods, such as counting stars in different directions, measuring the velocities of gas clouds, and observing the distribution of radio emission from hydrogen gas. Each method had uncertainties, and combining them required careful analysis and assumptions about the galaxy's symmetry and composition. By the late 20th and early 21st centuries, technological advances had greatly improved our ability to measure the Milky Way. Space-based telescopes like the Hubble Space Telescope provided clearer views, free from atmospheric distortion. Infrared observatories could peer through the dust to see stars near the galactic center. Radio telescopes mapped the distribution of hydrogen gas and traced the spiral arms. And large ground-based surveys began cataloguing millions of stars, measuring their positions, brightnesses, and velocities with unprecedented precision. The European Space Agency's Gaia mission, launched in 2013, represented a quantum leap in capability, measuring the precise positions and motions of over 1 billion stars and creating the most detailed three-dimensional map of the Milky Way ever produced. These advances led to refined estimates of the Milky Way's properties. The galaxy was thought to contain between 200 and 400 billion stars, with a total mass, including dark matter, of about 1 to 1.5 trillion times the mass of the Sun. The disk extended roughly 100,000 light-years in diameter, with the Sun located about 26,000 light-years from the center. The galaxy rotated, with stars in the solar neighborhood moving at about 220 kilometers per second around the galactic center, completing one orbit every 225 to 250 million years. These numbers became standard, appearing in textbooks, planetarium shows, and popular science articles. But as measurements improved and new techniques were developed, cracks began to appear in this comfortable consensus. Andromeda is now twice our size, not just bigger. To fully appreciate what the new measurements tell us about the Milky Way, it helps to compare our galaxy to others. Galaxies come in a wide variety of sizes, shapes, and masses, and understanding where the Milky Way fits in this spectrum provides context for interpreting the findings. Spiral galaxies, like the Milky Way, are characterized by flat, rotating disks with spiral arms and a central bulge. They range in size from small spirals with disks only 10,000 to 20,000 light-years across to giant spirals with disks exceeding 200,000 light-years. The Milky Way, with a disk diameter now estimated at 80,000 to 100,000 light-years, is in the large spiral category, but not among the very largest. Galaxies like NGC 6872, a barred spiral in the constellation Pavo, have disks extending over 500,000 light-years, making them among the largest known spiral galaxies. Mass is another key parameter. The Milky Way's total mass, including dark matter, is now estimated at 700 billion to 1 trillion solar masses. This places it in the upper range of spiral galaxy masses, but it is not exceptional. Many spiral galaxies have comparable masses, and some, like Andromeda, are more massive. The relationship between mass and size is not straightforward. More massive galaxies tend to have larger disks, but the relationship depends on factors like star formation efficiency, the amount of gas available, and the history of mergers. Elliptical galaxies, which are spheroidal or ellipsoidal in shape and lack the distinct disks and spiral arms of spirals, can be much more massive. Giant ellipticals like M87 in the Virgo cluster have total masses exceeding 10 trillion solar masses and contain trillions of stars. These galaxies form through the merger of multiple smaller galaxies and are found in the centers of galaxy clusters. The Milky Way, as a spiral, will eventually become an elliptical when it merges with Andromeda, but for now, it remains a disk-dominated system. The Milky Way is often described as a large spiral galaxy, one of the most massive in the local group, the small cluster of galaxies that includes Andromeda, Triangulum, and about 50 smaller dwarf galaxies. If the Milky Way is smaller and less massive than we thought, how does this change its standing among galaxies? And what does it tell us about galactic evolution more broadly? The local group is dominated by two large spirals, the Milky Way and Andromeda, also known as M31. For years, there has been debate about which galaxy is more massive. Early estimates suggested they were comparable, with the Milky Way possibly being slightly more massive. However, more recent measurements have consistently found that Andromeda is larger and more massive. Andromeda's disk extends farther, and its total mass, including dark matter, is estimated to be around 1.5 trillion solar masses, compared to the Milky Way's revised estimate of 700 billion to 1 trillion solar masses. If the lower end of the range is correct, Andromeda is nearly twice as massive as the Milky Way. This has implications for understanding the dynamics of the local group. The Milky Way and Andromeda are gravitationally bound and are moving toward each other. In about 4 to 5 billion years, they will collide and eventually merge to form a larger elliptical galaxy. The details of this merger, including the relative velocities and orientations of the galaxies, depend on their masses. If the Milky Way is less massive, the merger will be more asymmetric, with Andromeda dominating. Simulations of the collision can be updated to reflect the revised masses, providing more accurate predictions of the future evolution of the local group. Beyond the local group, the Milky Way can be compared to other galaxies in the universe. Galaxies span a vast range of sizes and masses, from dwarf galaxies containing only a few million stars to giant ellipticals with trillions of stars. The Milky Way is in the upper range of spiral galaxy masses, but it is not among the very largest. Galaxies like M87, a giant elliptical in the Virgo cluster, are far more massive, with total masses exceeding 10 trillion solar masses. By revising the Milky Way's mass downward, we are not reclassifying it as a small galaxy. It remains a substantial spiral, but we are recognizing that it is somewhat less massive than we assumed. We're the little brother in the local group. The revelation that the Milky Way is smaller than previously thought has a profound psychological impact on how we view our place in the cosmos. For decades, astronomers and the public alike thought of the Milky Way and Andromeda as roughly equal partners, two giant spiral galaxies dominating the local group of galaxies like twin titans. We were, if not quite equals, at least close enough in size and mass that the comparison was meaningful. The collision between the Milky Way and Andromeda in 4.5 billion years was framed as a clash of giants, a merger of peers, but the new measurements have upset this balanced picture. Andromeda, with its mass now estimated at about 1.5 to 2 trillion solar masses, is clearly the dominant galaxy in the local group. The Milky Way, at roughly 1 to 1.2 trillion solar masses, is significantly smaller, perhaps only 50 to 60% as massive. This isn't a clash of equals. It's a smaller galaxy being consumed by a larger one. We're not the giant we thought we were, we're the little brother. This realization has concrete implications for understanding the dynamics of the local group. The gravitational interaction between the Milky Way and Andromeda is not symmetric. Andromeda's stronger gravity dominates the evolution of the system. When the two galaxies collide, it will be Andromeda that pulls the Milky Way apart, not the other way around. Our galaxy will be tidally disrupted, its stars scattered across the merged system in streams and plumes, while Andromeda's core remains relatively intact. The resulting merged galaxy, Milky Way, will be more of a successor to Andromeda than to the Milky Way. The size discrepancy also affects the timeline of the collision. With a smaller Milky Way, the gravitational attraction between the two galaxies is somewhat weaker than previously calculated, which could mean the collision happens slightly later than the 4.5 billion years previously estimated. Alternatively, it could affect the trajectory of the collision, changing which parts of each galaxy collide first and altering the dynamics of the merger. These are subtle effects, but they matter for detailed predictions of what the collision will look like. Beyond the local group, the discovery that the Milky Way is smaller changes how we compare our galaxy to others in the universe. The Milky Way has often been used as a sort of standard reference galaxy, a typical large spiral that represents galaxies in general. But if we're smaller than we thought, we're less typical and more on the smaller end of large spirals. This matters for interpreting observations of distant galaxies. If we've been using the Milky Way as a yardstick, we need to recalibrate that yardstick. There's something almost poignant about the discovery that we're smaller than we thought. It's another in a long series of cosmological humiliations from Copernicus to Hubble, where humanity has learned that we're less central, less special, less important than we imagined. We're not at the center of the universe. We're not even in a particularly notable galaxy. We're in a perfectly decent spiral galaxy, yes, but one that's distinctly the junior partner in its local neighborhood. It's a humbling realization, but also a valuable one. Understanding our true place in the cosmos, however modest, is better than clinging to illusions of grandeur. Dark matter's invisible cage is smaller than we thought. Dark matter is central to any discussion of galactic mass and structure. It makes up the majority of the mass in galaxies, including the Milky Way, and its gravitational influence shapes the distribution of stars and gas. The discovery that the Milky Way is less massive has direct implications for our understanding of dark matter in and around our galaxy. The dark matter halo of the Milky Way extends far beyond the visible stars, likely out to several 100,000 light-years from the galactic center. Within this halo, the density of dark matter decreases with distance, following a profile that can be described by mathematical functions like the Navarro-Frank-White profile, commonly used in cosmological simulations. The exact shape of this profile, how steeply the density drops off, depends on the total mass of the halo and on the properties of dark matter itself. If the Milky Way's total mass is lower, the dark matter halo must be correspondingly less massive or less extended. This affects estimates of the local dark matter density, the amount of dark matter in the solar neighborhood. Experiments designed to directly detect dark matter particles rely on knowing the local density to predict how often dark matter particles should interact with detectors. A lower local density would mean fewer expected interactions, which could affect the interpretation of experimental results. Current estimates of the local dark matter density are around 0.3 to 0.4 GeV per cubic centimeter, equivalent to about 1 proton mass per cubic centimeter. If the Milky Way's halo is less massive, this density might be revised downward, though the effect is modest because the solar neighborhood is deep within the halo, where density measurements are more robust. The distribution of dark matter also affects the dynamics of satellite galaxies and stellar streams. Stellar streams are elongated structures formed when small galaxies or globular clusters are tidally disrupted by the Milky Way's gravity, leaving trails of stars along their former orbits. By studying the orbits and properties of these streams, astronomers can map the gravitational potential of the galaxy and infer the distribution of dark matter. Several streams have been identified using Gaia data, and they provide powerful constraints on the halo's shape and mass. The fact that these streams are consistent with a somewhat less massive halo supports the revised estimates of the Milky Way's mass. Dark matter may also play a role in the structure of the disk itself. Some models propose that a dark disk, a flattened component of dark matter aligned with the stellar disk, could exist. This dark disk would contribute to the local dark matter density and could affect the motions of stars and gas in the disk. The evidence for a dark disk is mixed, and the revised estimates of the Milky Way's mass do not strongly favour or disfavour its existence. However, understanding whether such a component exists is important for a complete picture of the galaxy's structure. The nature of dark matter itself remains one of the great mysteries in physics. We know it exists because of its gravitational effects, but we do not know what it is made of. Leading candidates include weakly interacting massive particles, or WIMPs, axions, and sterile neutrinos. Each of these candidates has different properties and would produce different distributions of dark matter in galaxies. By refining our measurements of the Milky Way's dark matter halo, we provide better constraints on these theories. For example, if dark matter particles interact with each other through forces beyond gravity, it could affect the density profile of the halo, making it more diffuse or creating distinctive features. The revised estimates of the halo's size and mass help narrow the range of possibilities, what it means for the Sun's neighbourhood. One question that arises from the discovery that the Milky Way is smaller is whether it affects our understanding of the Sun's position within the galaxy. For decades, the Sun has been described as being about halfway out from the centre, located in a minor spiral arm called the Orion Spur, or Orion Arm, between two major spiral arms, Sagittarius and Perseus. If the galaxy is more compact, does this mean the Sun is in a different relative position? The answer is nuanced. The Sun's absolute distance from the galactic centre has been measured with increasing precision and is now known to be about 26,000 light-years, with an uncertainty of only a few hundred light-years. This measurement is based on multiple methods, including observations of stars orbiting near the supermassive black hole at the galactic centre, and measurements of the parallax and proper motion of stars along the line of sight to the centre. These methods are independent of the overall size of the galaxy, so the Sun's distance from the centre does not change significantly with the new estimates. However, the Sun's position relative to the edge of the disk does change. If the disk extends to about 90,000 to 100,000 light-years in diameter, then the Sun, at 26,000 light-years from the centre, is roughly 58% of the way out from the centre to the edge. But if the disk extends only to about 80,000 to 90,000 light-years, then the Sun is proportionally farther out, closer to 2/3 of the way from the centre to the edge. This might seem like a minor difference, but it has implications for understanding the Sun's environment and history. Stars in the outer regions of a galaxy typically have different properties from those in the inner regions. Outer disk stars tend to be older, have lower metallicity, meaning fewer heavy elements, and are more influenced by interactions with the halo and with satellite galaxies. If the Sun is relatively farther out than we thought, it suggests that the solar neighbourhood might have some characteristics typical of the outer disk. However, observations of nearby stars do not strongly support this. The Sun's metallicity is typical of stars at similar distances from the galactic centre, and the stellar population around the Sun is consistent with the traditional picture of the disk. Another aspect is the Sun's motion through the galaxy. The Sun orbits the galactic centre with a velocity of about 220 kilometers per second, taking roughly 225 to 250 million years to complete one orbit. This orbital period, sometimes called a galactic year, is determined by the mass distribution interior to the Sun's orbit. If the galaxy is less massive overall, but the mass interior to the Sun's orbit is similar, then the Sun's orbital period does not change much. However, if the distribution of mass is different, there could be subtle effects on the Sun's orbit and on the motions of nearby stars. The Sun also has a peculiar velocity relative to the average motion of stars in the solar neighborhood. It is moving slightly faster than the average toward the constellation Hercules, and it oscillates up and down relative to the galactic plane with a period of about 60 million years. These motions are influenced by the gravitational potential of the disk and halo. If the galaxy's structure is somewhat different, the details of these oscillations might change, though the effects would be small. One interesting question is whether the Sun's position has any implications for the history of life on Earth. Some researchers have proposed that the Sun's passage through spiral arms, where there are more massive stars and supernovae, could affect Earth's climate or biosphere through increased cosmic rays or other mechanisms. If the spiral structure is different from what we thought, the timing and frequency of spiral arm passages might change, though current evidence suggests these effects, if they exist, are subtle. Sagittarius A*, the 4 million solar mass monster at our core. The galactic center, located about 26,000 light-years from the Sun, in the direction of the constellation Sagittarius, is one of the most fascinating and extreme environments in the Milky Way. It is a region of intense activity, with a supermassive black hole, dense star clusters, powerful magnetic fields, and ongoing star formation, despite the harsh conditions. Sagittarius A*, the supermassive black hole at the galaxy's heart, is surrounded by a cluster of stars, some of which orbit incredibly close to the black hole. These stars, designated as stars, have been monitored for decades, and their orbits have been mapped with exquisite precision. The star, S2, for example, has an orbital period of about 16 years and comes within about 17 light-hours of the black hole at its closest approach, roughly 4 times the distance from the Sun to Neptune. Observations of S2's orbit have confirmed predictions of general relativity, such as the gravitational redshift of light escaping the strong gravitational field and the precession of the orbit's ellipse. The environment around Sagittarius A times is also rich in gas and dust, though the black hole itself is not currently consuming large amounts of material. Occasionally, clouds of gas pass close to the black hole, and astronomers watch to see if they are torn apart and accreted. One such event was the passage of the gas cloud G2 in 2014, which survived its close encounter largely intact, suggesting it may have had a star at its core, providing additional gravitational support. The galactic center also contains several massive star clusters, including the Arches and Quintuplet clusters, which are among the densest and most massive young star clusters in the galaxy. These clusters contain dozens of massive, luminous stars and are located within a few hundred light-years of the galactic center. The formation of such massive clusters in the crowded and turbulent environment near the black hole is remarkable and suggests that star formation processes there are different from those in the disk. The central region is also home to intense radio and infrared emission. The radio source Sagittarius A, which encompasses Sagittarius A*, is embedded in a complex of emission features including Sagittarius A East, a supernova remnant, and Sagittarius A West, a spiral-shaped structure of ionized gas. Infrared observations penetrate the dust that obscures visible light, revealing the dense stellar populations and the intricate structures of gas and dust. Magnetic fields near the galactic center are exceptionally strong, estimated to be thousands of times stronger than in the solar neighborhood. These fields influence the dynamics of gas and the propagation of cosmic rays, and they may play a role in the outflows and jets observed in some active galactic nuclei. Understanding the magnetic field structure near the galactic center is an active area of research, with observations using radio polarimetry and other techniques. The galactic center is also a source of high-energy gamma rays, detected by instruments like the Fermi Gamma Ray Space Telescope. The origin of this gamma ray emission is debated. Some of it likely comes from cosmic rays interacting with gas, but there may also be contributions from pulsars, supernova remnants, or even dark matter annihilation. The possibility that dark matter particles are annihilating near the galactic center, where their density is highest, is particularly intriguing and has motivated searches for specific gamma ray signatures that would indicate this process. The mysterious bar, a hidden structure shaping our galaxy, hidden in plain sight at the heart of the Milky Way, is one of its most important and least understood structures, a massive bar of stars stretching across the galactic center. This bar, first discovered in the 1990 seconds through infrared observations that could penetrate the dust obscuring the center, is not just a minor feature, but a fundamental component of the galaxy's anatomy, influencing the orbits of billions of stars and playing a crucial role in the galaxy's evolution. The bar is enormous, extending about 27,000 light-years from end to end, roughly half the radius of the entire galactic disk. It's composed of old, red stars that orbit in elongated paths aligned with the bar's major axis, creating a density wave that rotates around the galactic center like the hands of a clock. From our position in the galaxy, we see the bar almost edge on, which is why it took so long to discover. If we were looking at the Milky Way from above, the bar would be obvious, a bright, elongated structure cutting across the center. Barred spiral galaxies like the Milky Way are extremely common, accounting for about 2/3 of all spiral galaxies in the universe. The bar forms through a gravitational instability in the disk. Regions of slightly higher density attract more stars, which increases the density further, creating a feedback loop that results in a prominent bar structure. Once formed, the bar is remarkably stable, rotating as a solid body for billions of years. The bar has profound effects on the dynamics of the galaxy. Stars and gas clouds that interact with the bar can have their orbits dramatically altered, either being flung outward to larger radii or driven inward toward the galactic center. This process, called dynamical friction, is thought to be responsible for funneling gas toward the center, where it feeds the supermassive black hole Sagittarius A times and triggers bursts of star formation in the central regions. The bar is, in a sense, the engine that drives the galactic center's activity. Understanding the bar's structure and evolution is crucial for measuring the Milky Way's size and mass, because the bar affects the distribution of stars and the overall gravitational potential of the galaxy. Earlier models that didn't properly account for the bar's influence could have led to incorrect estimates of the galaxy's total mass. Gaia's observations of stellar motions in the galactic center have provided new insights into the bar's properties, including its rotation speed, shape, and age, all of which feed into more accurate models of the galaxy as a whole. One of the most fascinating aspects of the bar is that it may not be permanent. Simulations suggest that bars can be disrupted by interactions with other galaxies, or by changes in the distribution of dark matter in the galactic halo. The Milky Way's bar could weaken or dissolve over the next few billion years, especially as the galaxy approaches its collision with Andromeda. In a sense, we're fortunate to be alive during an era when the Milky Way has a prominent bar. Future observers in Milkomeda won't see such a structure. The discovery and characterization of the Milky Way's bar is a perfect example of how our understanding of the galaxy has evolved. For centuries, we thought we lived in a simple, symmetric, spiral galaxy. Now we know our galaxy is barred, warped, and far more complex than the idealized pictures in textbooks. Each new discovery adds a layer of complexity and makes the Milky Way more interesting, even as it makes our galaxy seem less grand in terms of sheer size. Why measuring from inside is like mapping a forest from a tree. Measuring the Milky Way from inside, it presents unique challenges that do not arise when studying external galaxies. These challenges help explain why our estimates of the galaxy's size and mass have evolved over time, and why recent findings are significant. One major challenge is extinction, the absorption and scattering of light by interstellar dust. Dust is concentrated in the plane of the galactic disk, especially along the spiral arms where star formation occurs. This dust blocks visible light, making it difficult to see stars on the far side of the galaxy, or even to see the galactic center directly in optical wavelengths. Infrared and radio observations can penetrate dust more effectively, but they measure different properties and require careful calibration. Early estimates of the galaxy's size were biased by extinction, leading astronomers to underestimate how far the disk extended. Another challenge is the geometry of our vantage point. Observing the galaxy from inside means we see it edge on in some directions and face on in others. This makes it difficult to determine the overall shape and structure. For example, the spiral arms of the Milky Way are hard to map because we are embedded in one of them, and we cannot step back to see the full pattern. Astronomers have used various techniques to overcome this, such as mapping the distribution of young stars and HII regions, ionized hydrogen clouds, that trace the spiral arms, but uncertainties remain. Measuring distances is perhaps the most fundamental challenge. Without accurate distances, we cannot determine the size of the galaxy or the distribution of its components. Parallax measurements provide direct geometric distances, but they are limited to relatively nearby stars. For more distant objects, astronomers must rely on standard candles or other indirect methods, each with its own uncertainties and systematic errors. The Gaia mission has dramatically improved distance measurements out to several thousand light-years, but beyond that, uncertainties increase. Determining the total mass of the galaxy is also difficult, because most of the mass is dark matter, which cannot be seen directly. Astronomers infer the presence and distribution of dark matter from its gravitational effects on stars, gas, and satellite galaxies. This requires careful modeling of the galaxy's dynamics, including assumptions about equilibrium, symmetry, and the behavior of different components. If these assumptions are incorrect, the inferred mass could be wrong. The revised estimates of the galaxy's mass reflect improved observations and more sophisticated models, but they still carry uncertainties. The Milky Way is not an isolated system. It is part of the local group and interacts gravitationally with Andromeda and other nearby galaxies. These interactions can affect the orbits of stars and satellites in the outer regions of the galaxy, complicating the interpretation of observations. For example, the Magellanic Clouds, the two largest satellite galaxies of the Milky Way, are thought to be on their first pass around the galaxy, and their gravitational influence may have disturbed the outer disk and halo. Understanding these interactions is important for accurately modeling the galaxy's structure. Variability and evolution also introduce challenges. Stars are born, evolve, and die, and the distribution of stellar populations changes over time. Gas is converted into stars, and stars return gas and heavy elements to the interstellar medium through winds and supernovae. The galaxy's structure today is a snapshot of an ongoing process, and understanding that process requires not just measuring the current state, but also reconstructing the history. This is where computer simulations and models of galactic evolution come into play, helping to interpret the observations and infer the underlying physics. Finally, there is the challenge of synthesis, combining observations from different wavelengths and different types of objects into a coherent picture. The Milky Way can be studied in visible light, infrared, radio, X-rays, and gamma rays, each revealing different aspects. Stars, gas, dust, and cosmic rays all contribute to the galaxy's structure and dynamics, and integrating all this information requires sophisticated analysis. The recent finding that the galaxy is smaller is the result of synthesizing diverse observations and recognizing patterns that point to a more compact structure, the Magellanic Clouds. Our closest companions are colliding with us. Look up at the night sky from the southern hemisphere, and you'll see two fuzzy patches of light that look like detached pieces of the Milky Way. These are the Large and Small Magellanic Clouds, the two closest galaxies to the Milky Way, and among our most important neighbours in understanding our own galaxy's size and mass. Named after the explorer Ferdinand Magellan, whose crew observed them during the first circumnavigation of the Earth, these dwarf irregular galaxies have been known to humanity for thousands of years, but have only recently revealed their true nature and their dramatic fate. The Large Magellanic Cloud, or LMC, lies about 160,000 light-years away, while the Small Magellanic Cloud, or SMC, is roughly 200,000 light-years distant. They're much smaller than the Milky Way. The LMC contains about 30 billion stars compared to our 200 to 400 billion, but they're large enough to retain their own structure and identity as galaxies in their own right. They orbit the Milky Way in complex paths that bring them close to our galaxy every few 100 million years, and those close encounters have profound effects on all three galaxies. What makes the Magellanic Clouds especially important for measuring the Milky Way is that they serve as test particles in our galaxy's gravitational field. By observing their positions, distances, and velocities, astronomers can infer the mass distribution of the Milky Way, much like watching a planet orbit the Sun tells us about the Sun's mass. Gaia's observations of stars in the Magellanic Clouds have provided the most accurate measurements ever of their motions through space, and those measurements fed directly into the revised estimates of the Milky Way's total mass. But the Magellanic Clouds are not just passive probes, they're actively interacting with the Milky Way in ways that are reshaping all three galaxies. Tidal forces from the Milky Way's gravity are pulling streams of gas from the Magellanic Clouds, creating enormous filaments of hydrogen that trail behind them like the tail of a comet. This gas, known as the Magellanic Stream, stretches across 200 degrees of the sky, more than half the celestial sphere, and contains enough material to make hundreds of millions of new stars. Recent studies have revealed that the Magellanic Clouds are on a collision course with the Milky Way, though not in the sense you might imagine. Rather than smashing into the main disk, the LMC and SMC will likely pass through the Milky Way's halo over the next few 100 million years, stirring up the dark matter and potentially triggering gravitational interactions that disturb the orbits of stars in the outer parts of our galaxy. Eventually, billions of years from now, they will be fully absorbed, their stars scattered throughout the Milky Way's halo, their gas stripped away, and added to our galaxy's supply of star-forming material. The presence of the Magellanic Clouds also complicates the question of the Milky Way's size. Should we count the Magellanic Stream as part of the Milky Way, since it's gas that's being accreted from the clouds? What about the tidal streams of stars that have already been pulled from the clouds and now orbit independently? These questions don't have simple answers, but they highlight how galaxy boundaries are fuzzy and how interactions with satellites blur the distinction between separate galaxies. For the purposes of measuring the Milky Way's mass, astronomers typically don't count the Magellanic Clouds themselves, even though they're gravitationally bound to our galaxy. But the ongoing interaction between the clouds and the Milky Way must be accounted for in models of the galaxy's dynamics. The LMC in particular is massive enough that its gravity affects the distribution of dark matter in the Milky Way's halo, creating a wake of disturbed material that extends for hundreds of thousands of light years. Accounting for this interaction is crucial for getting accurate mass estimates, and it's one of the reasons recent estimates have converged on smaller values than older studies that didn't fully account for the Magellanic Cloud's influence. JWST and future missions will refine the numbers. The discovery that the Milky Way is smaller than we thought is based on the best data currently available, but the story is far from over. Future observations and missions will continue to refine our understanding, potentially confirming the new estimates or revealing further surprises. Let's look at some of the key projects that will contribute to our knowledge of the galaxy in the coming years. The Gaia mission is still ongoing, and future data releases will provide even more precise measurements. Gaia's third data release, published in 2022, included astrometry, photometry, and spectroscopy for nearly 2 billion sources. Future releases will extend the mission's timeline, improve the precision of measurements, and add new types of data, such as observations of variable stars, binary stars, and asteroids. With each data release, astronomers can refine their models of the galaxy's structure and dynamics, potentially revealing new features or confirming the revised estimates of size and mass. The Vera C. Rubin Observatory, formerly known as LSST, Large Synoptic Survey Telescope, is scheduled to begin operations in the mid-2022. This ground-based telescope will survey the entire visible sky repeatedly, creating a time-lapse movie of the universe. For the Milky Way, Rubin will provide deep, wide-area imaging that will reveal faint stars, stellar streams, and other structures in the halo. It will also detect transient events like supernovae, stellar flares, and asteroid occultations, adding to our understanding of the galaxy's dynamics and evolution. The Nancy Grace Roman Space Telescope, NASA's next flagship astrophysics mission, is planned for launch in the mid-2022. Roman will have a wide field of view and will conduct infrared surveys of the galactic bulge and disk. Its observations will complement Gaia by reaching farther into the dust-obscured regions of the galaxy and by providing near-infrared photometry and spectroscopy for millions of stars. Roman's microlensing survey will also detect planets, brown dwarfs, and black holes in the galaxy, adding to our census of the galaxy's contents. The Square Kilometre Array, SKA, an international radio telescope project, is under construction in Australia and South Africa. When completed, the SKA will be the world's most powerful radio telescope, capable of mapping the distribution of neutral hydrogen gas throughout the Milky Way and beyond. By tracing the hydrogen gas, which extends farther from the galactic centre than most stars, the SKA will provide a complete picture of the galaxy's disk and help determine its exact size. Ground-based spectroscopic surveys are also expanding. Projects like Apogee, Apache Point Observatory, Galactic Evolution Experiment, and GALA Galactic Archaeology with Hermes are collecting spectra for millions of stars, measuring their velocities, temperatures, and chemical compositions. These surveys are revealing the detailed structure of the disk, bulge, and halo, and they are tracing the histories of different stellar populations. Future surveys will extend this work, reaching even fainter and more distant stars. Gravitational wave observatories, while primarily focused on detecting mergers of black holes and neutron stars, may also provide information about the Milky Way. If a neutron star merger or supernova occurs within the galaxy, the gravitational waves could be detected, providing a new way to probe the galaxy's stellar populations and dynamics. The LISA mission, planned for launch in the 2032, will detect lower frequency gravitational waves and may be sensitive to sources within the galaxy. Computer simulations will continue to play a crucial role. As computing power increases, simulations of galaxy formation and evolution become more detailed and realistic. By comparing the properties of simulated galaxies to observations of the Milky Way, astronomers can test their understanding of the physical processes that shape galaxies and refine their models. Future simulations will incorporate more physics, such as the effects of magnetic fields, cosmic rays, and the detailed chemistry of star formation, providing more accurate predictions to compare with observations. All of these projects will contribute to a more complete and accurate picture of the Milky Way. They will test the revised estimates of size and mass, and they may reveal new aspects of the galaxy's structure and history that we have not yet imagined. The process of discovery is ongoing, and each new observation brings us closer to a full understanding of our cosmic home. The Andromeda collision, timing might be different now. One of the most dramatic implications of the Milky Way's smaller size is that it could affect the timing and dynamics of our galaxy's collision with Andromeda. For years, astronomers have confidently stated that the two galaxies will collide in about 4.5 billion years, but that estimate was based on models that assumed certain values for the masses of both galaxies. With the Milky Way now known to be less massive, the gravitational attraction between the two galaxies is weaker, which could push back the collision timeline or alter its trajectory in significant ways. The collision timeline is determined by several factors. The current distance between the galaxies, about 2.5 million light-years, their current velocities relative to each other, approximately 110 kilometers per second of approach velocity, and the total mass of the system, which determines how much the galaxies accelerate toward each other due to gravity. If the total mass is lower than previously thought, the acceleration is weaker and it takes longer for the galaxies to come together. Computer simulations incorporating the new mass estimates suggest that the collision could be delayed by several 100 million years, pushing the first close encounter to perhaps 5 billion years from now, rather than 4.5 billion. This might not sound like a big difference in the context of billions of years, but it's actually quite significant. In 500 million years, the Sun will be noticeably brighter, Earth will be significantly hotter, and the timeline for the end of habitability on our planet could be affected. More importantly for galactic dynamics, even small changes in the timing can have cascading effects on how the collision unfolds, which parts of each galaxy collide first, how much energy is released, and what the final merged structure looks like. The revised mass estimates also affect predictions of the collision's violence. A smaller Milky Way means there's less total momentum in the system, which could result in a somewhat less energetic collision. This doesn't mean it will be gentle. Galaxy collisions are never gentle, but it could mean fewer extreme tidal disruptions, less gas compression, and possibly fewer starbursts triggered by the interaction. The final merged galaxy, Milkomeda, might be somewhat less massive than previous estimates suggested, though still a giant elliptical galaxy by any standard. There's also the question of how the collision affects the smaller galaxies in the local group, the dwarf satellites orbiting both the Milky Way and Andromeda. With a smaller Milky Way, our satellite galaxies are less tightly bound to us, which means some of them might be captured by Andromeda during the collision rather than remaining part of the Milky Way's system. The dynamics of these interactions are complex and depend on the precise trajectories of each satellite, but the overall effect is that the collision could redistribute the small galaxies of the local group in ways that differ from earlier predictions. One thing that hasn't changed, despite the revised mass estimates, is the inevitability of the collision. The Milky Way and Andromeda are gravitationally bound to each other, and no known force can prevent them from eventually merging. The discovery that the Milky Way is smaller doesn't alter this fundamental fact. It only adjusts the details of when and how the collision will occur. In the grand scheme of cosmic evolution, these are relatively minor refinements, but for astronomers trying to understand the future of our galactic neighborhood, they're important details that bring our predictions closer to reality. Perhaps most importantly, the revised collision timeline serves as a reminder of how interconnected galactic properties are. Knowing the exact mass of the Milky Way matters not just for understanding our own galaxy, but for predicting the future of the entire local group. Every new measurement, every revision to our understanding, ripples out to affect dozens of related questions. Getting the Milky Way's size right is crucial for getting everything else right, and thanks to missions like Gaia, we're finally approaching that goal. Why getting our size right changes everything we know. The realization that the Milky Way is smaller and less massive than previously thought has implications for how we think about our place in the cosmos. Our cosmic address, the series of increasingly large structures to which we belong, defines our context and our relationship to the wider universe. Let's trace this address and see how the new findings affect it. We start with Earth, the third planet from the Sun in the solar system. The solar system is located in the Orion Arm, a minor spiral arm of the Milky Way, about 26,000 light-years from the galactic center. This places us in the suburban outskirts of the galaxy, neither at the center nor at the edge. The Sun orbits the galactic center once every 225 to 250 million years, carrying the solar system and all its planets along for the ride. The Milky Way itself is part of the local group, a small cluster of galaxies that includes about 50 known members. The two largest members are the Milky Way and Andromeda, with the Triangulum galaxy a distant third. The local group spans about 10 million light-years across, and it is gravitationally bound, meaning its members orbit around a common center of mass. The revised estimate of the Milky Way's mass affects the dynamics of the local group, making Andromeda proportionally more dominant. The local group, in turn, is part of the Virgo supercluster, a larger structure containing thousands of galaxies spread across about 110 million light-years. The Virgo supercluster is dominated by the Virgo cluster, a massive concentration of galaxies located about 50 to 60 million light-years from us. The local group is on the outskirts of the Virgo supercluster, and it is slowly falling toward the Virgo cluster under the influence of its gravity. As we conclude this exploration of the Milky Way's revised size, it's worth reflecting on what these discoveries mean from a human perspective. Why do we care about the size and structure of our galaxy? What does it tell us about ourselves and our place in the universe? On one level, understanding the Milky Way is simply an intellectual pursuit, driven by curiosity and the desire to know. Humans have always looked up at the night sky and wondered what lies beyond. The Milky Way is our cosmic home, and understanding it is a natural extension of our desire to understand our surroundings, whether that's our immediate environment on Earth or the vastness of space. On another level, studying the Milky Way connects us to the cosmos in a profound way. We are not separate from the galaxy, but a part of it. The atoms in our bodies were created in stars, and those stars are members of the Milky Way. The Sun, our source of light and energy, is one of hundreds of billions of stars in the galaxy, and it carries us through space on its orbit around the galactic center. Understanding the Milky Way helps us understand our origins and our place in the grand scheme of cosmic evolution. The discovery that the Milky Way is smaller also reminds us that our knowledge is always evolving. What we know about the universe is based on the best observations and theories available at any given time, but it is always subject to revision. This is not a weakness of science, but one of its greatest strengths. Science is self-correcting, constantly testing its ideas against new data and revising when necessary. The willingness to change our minds in the face of new evidence is what allows science to progress and to give us an increasingly accurate picture of reality. The discovery that shook astronomy in 2020. When the results were first published in late 2020 inches, the monthly notices of the Royal Astronomical Society, the astronomy community reacted with a mixture of surprise and excitement. The paper, authored by an international team of researchers led by Dr. Alice Deason from Durham University, presented a comprehensive analysis of Gaia data combined with observations of satellite galaxies and theoretical modelling. Their conclusion was unequivocal. The Milky Way's total mass is approximately 1 trillion solar masses, give or take 200 billion, significantly less than the 1.5 to 2 trillion solar masses that had been the consensus estimate for years. The announcement didn't come out of nowhere. Hints that something was wrong with the Milky Way's mass estimates had been accumulating for years. Studies of the galaxy's rotation curve had shown anomalies that didn't quite fit the standard models. Observations of satellite galaxies had revealed orbital velocities that seemed inconsistent with a very massive Milky Way. Measurements of the galaxy's gravitational influence on nearby structures suggested a more modest mass, but these were all indirect hints, subject to alternative interpretations and plagued by uncertainties. What Gaia provided was direct, precise measurements of stellar motions that left little room for doubt. The key to the breakthrough was Gaia's ability to measure not just the positions of stars, but their three-dimensional velocities through space. This required observing the same stars multiple times over several years to track their tiny motions across the sky, a technique called proper motion measurement, as well as using spectroscopy to measure their velocities toward or away from us via the Doppler shift. Combining these measurements gave astronomers a complete picture of how stars move in the outer regions of the galaxy, and that picture revealed a mass distribution that was smaller and more compact than expected. One of the most striking findings was that the stellar halo, the roughly spherical cloud of old stars surrounding the galactic disk, is significantly less massive than previous models suggested. Earlier estimates had placed the halo's mass at about 100 billion solar masses, but the new data indicated it's closer to 30 to 50 billion solar masses. This might seem like a detail, but the halo's mass is directly linked to the total mass of the galaxy, because the halo stars orbit in the gravitational potential created by all the mass, visible and dark, within their orbital radii. A less massive halo means less total mass. The reaction among astronomers ranged from vindication for those who had long suspected the Milky Way was overestimated, to surprise among those who had based their research on the larger mass estimates. For some, the discovery required revisiting years of previous work, recalculating results, and updating models. For others, it opened up new research opportunities, explaining anomalies in the data that had been puzzling and providing a more consistent framework for understanding the local group. The discovery also highlighted the remarkable progress in observational astronomy over just the past decade. The leap in capability from pre-Gaia observations to Gaia's all-sky survey is staggering. Before Gaia, measuring the distance to a star 100,000 light-years away was nearly impossible. Now, Gaia routinely measures distances and velocities for stars at those distances with errors of just a few percent. This kind of precision transforms astronomy from an art of educated guesses into a rigorous science of direct measurement, and the Milky Way's mass is just one of many fundamental parameters that Gaia has helped us pin down with unprecedented accuracy. What it means for understanding dark matter halos, The discovery that the Milky Way is smaller than we thought has profound implications for our understanding of dark matter, the invisible substance that makes up most of the mass in galaxies. Dark matter doesn't emit, absorb, or reflect light, so we can only detect it through its gravitational effects on visible matter. By measuring how fast stars orbit the galaxy at different radii, astronomers can infer the distribution of all mass, including dark matter, and use that to constrain the properties of dark matter particles and the shape of dark matter halos. The revised mass estimate for the Milky Way means that the dark matter halo is both less massive and less extended than previous models suggested. Earlier models often assumed that the dark matter halo extended out to 300,000 light-years or more from the galactic center, gradually fading into the intergalactic medium. The new data suggests the densest part of the halo ends closer to 130,000 to 150,000 light-years, with only tenuous wisps of dark matter beyond that. This has important implications for direct detection experiments trying to discover dark matter particles. These experiments, located in deep underground laboratories to shield them from cosmic rays, are looking for the rare interactions between dark matter particles and normal matter. The rate of such interactions depends on the local density of dark matter, which depends on the overall structure of the Milky Way's dark matter halo. If the halo is less massive and more compact than we thought, it could affect predictions of how many dark matter particles pass through the Earth, and thus how often they should be detected. The shape of the dark matter halo also matters for understanding how galaxies form and evolve. Simulations of galaxy formation predict that dark matter halos should have a specific density profile, with density decreasing with distance from the center, following a mathematical relationship called the Navarro-Frenk-White profile, or NFW profile. Real galaxies, however, often show deviations from this idealized profile, especially in their inner regions. The Milky Way's halo, with its more compact structure, provides crucial data for testing and refining these models. One particularly interesting aspect of the revised halo structure is what it tells us about the history of the Milky Way. Dark matter halos grow over time through the accretion of smaller halos as galaxies merge and interact. Each merger leaves its imprint on the structure of the combined halo. The fact that the Milky Way's halo is smaller and more compact than expected could mean our galaxy has had fewer major mergers than galaxies like Andromeda, which has clearly consumed multiple large satellites. This would make the Milky Way more representative of galaxies that have had relatively quiet merger histories, which is valuable for understanding the diversity of galaxy evolution pathways. The discovery also affects our understanding of the local group's dynamics. The total mass of the local group, which includes the Milky Way, Andromeda, and dozens of smaller galaxies, can be estimated from the motions of galaxies within the group. If the Milky Way is less massive, the total mass of the local group must be revised downward as well, which has implications for understanding how the group formed and how it will evolve in the future. Some models of local group dynamics will need to be updated to account for the new mass estimates. Finally, the revised dark matter halo has implications for understanding cosmic structure on larger scales. The Milky Way is often used as a template for understanding galaxies at high redshifts, distant galaxies we observe as they were billions of years ago. If the Milky Way's dark matter halo is smaller than we thought, we might need to revise our interpretations of observations of distant galaxies, affecting our understanding of how galaxies and their dark matter halos evolve over cosmic time. The Sun's galactic orbit reconsidered. Understanding the Sun's motion through the Milky Way is not just an academic exercise. It has practical implications for understanding the history of Earth's climate, the bombardment of our solar system by comets, and even the distribution of molecular clouds that could affect star formation. The Sun orbits the galactic center at a distance of about 26,000 light-years, traveling at a velocity of approximately 220 kilometers per second. This means it takes about 225 to 250 million years to complete one orbit, a timescale called a galactic year or cosmic year. But the Sun doesn't just orbit in a perfect circle. It also bobs up and down through the galactic plane, oscillating with a period of about 30 million years. This vertical motion carries the Sun through regions of varying stellar and gas density, and some researchers have speculated that passages through the galactic plane, where the density is highest, could gravitationally disturb the Oort cloud of comets surrounding the solar system, sending a shower of comets into the inner solar system. These comet impacts could, in principle, affect Earth's climate or even trigger mass extinctions, though this idea remains controversial. The discovery that the Milky Way is less massive changes the details of the Sun's orbit. With less total mass inside the Sun's orbit, the gravitational force pulling the Sun toward the galactic center is weaker, which affects the shape of the orbit and the period of oscillation through the plane. The changes are subtle, perhaps a few percent in the orbital period or the oscillation frequency, but they're detectable and significant for detailed studies of the Sun's orbital history. One interesting consequence is that it allows us to better reconstruct where the Sun was in the past. By tracing the Sun's orbit backward in time, accounting for the gravitational potential of the galaxy, we can estimate where the Sun formed and how it has migrated over the past 4.5 billion years. The Sun almost certainly didn't form at its current location. Most stars drift inward or outward over time due to gravitational interactions with other stars and with spiral density waves. The new mass estimates provide a more accurate gravitational potential, which makes these backward in time calculations more reliable. There's also the question of the Sun's future orbit. Over the next few billion years, as the Sun continues to orbit the galaxy, will it stay at roughly its current distance from the center, or will it migrate significantly? The answer depends on the galaxy's mass distribution and how it evolves over time, especially as the Milky Way approaches its collision with Andromeda. A smaller Milky Way means somewhat different orbital dynamics, and while the Sun's orbit won't change dramatically in the near term, over timescales of billions of years, the differences add up. The Sun's orbital motion also affects our measurements of the cosmic microwave background, the relic radiation from the Big Bang. Because the Sun is moving at 220 kilometers per second relative to the galactic center, and the galactic center is moving relative to the local group, and the local group is moving relative to the cosmic microwave background rest frame, our motion introduces a Doppler shift in the CMB that makes it appear slightly hotter in the direction we're moving and slightly cooler in the opposite direction. Accurately accounting for all these motions requires knowing the gravitational potential of the galaxy, which now has been revised. The corrections are small, but for precision cosmology, even small corrections matter. In a broader sense, understanding the Sun's orbit connects us to the larger story of galactic evolution. The Sun is just one of 200 to 400 billion stars in the Milky Way, each with its own orbit, each contributing to the collective gravitational potential that shapes the galaxy. By studying the Sun's orbit in detail, we learn about the structure and history of the entire galaxy. And by getting that orbit right, accounting for the revised mass estimates, we're refining our understanding of our cosmic home and our place within it. How the new size changes galactic structure. The discovery that the Milky Way is smaller than we thought has important implications for our understanding of galactic structure and dynamics. Galaxies are complex systems, with stars, gas, dust, and dark matter all interacting through gravity and other forces. The size and mass of a galaxy determine many of its properties, from how fast stars orbit to how efficiently it forms new stars. By revising our estimates of the Milky Way's size and mass, we need to reconsider many aspects of how our galaxy works. One immediate implication concerns the distribution of stars in the galactic disk. If the disk is more compact, then the density of stars at a given distance from the Sun is higher than we thought, at least in the outer regions. This has consequences for understanding star formation history. A more compact disk might indicate that star formation has been more concentrated toward the inner regions, or that stars in the outer disk have different properties or origins than we assumed. It also affects estimates of the total number of stars in the galaxy. With a smaller disk, the total stellar population might be toward the lower end of previous estimates, perhaps closer to 200 billion stars, rather than 400 billion. The shape of the disk is also relevant. The Milky Way's disk is not perfectly flat but has a warp, a twist that causes the outer parts of the disk to deviate from the plane defined by the inner regions. This warp has been known for decades, but its cause is still debated. Some models suggest it results from gravitational interactions with satellite galaxies, while others propose it is due to the distribution of dark matter or to the galaxy's rotation. If the disk is more compact, the warp might have a different explanation or might be more pronounced relative to the overall size. Understanding the warp is important because it affects how we measure distances to stars and how we interpret observations of the outer disk. The spiral arms of the Milky Way are another area of interest. Spiral arms are regions of higher stellar density and active star formation, visible in many disk galaxies. The Milky Way has several major spiral arms, but determining their exact structure from our vantage point inside the galaxy is challenging. If the disk is smaller, the spiral arms might be more tightly wound or might extend less far than we thought. This has implications for understanding the processes that create and maintain spiral structure, which involve density waves, gravitational instabilities, and feedback from star formation. The galactic halo, the roughly spherical region surrounding the disk, contains old stars, globular clusters, and a diffuse population of stars that are chemically distinct from those in the disk. The halo also contains the bulk of the galaxy's dark matter. If the Milky Way is less massive, the halo must be correspondingly smaller or less dense. This affects our understanding of how the halo formed, which is thought to involve the accretion and disruption of smaller satellite galaxies over billions of years. A smaller halo might mean fewer such accretion events or a different timeline for the galaxy's assembly. What the smaller size means for stellar populations. The structure and size of the Milky Way affect the populations of stars within it, and conversely, studying stellar populations provides insights into the galaxy's history and evolution. The discovery that the galaxy is smaller has implications for how we understand the distribution and properties of different types of stars. Stars in the Milky Way can be broadly divided into populations based on their age, chemical composition, and kinematics. Population I stars are young, metal-rich, and found primarily in the disk, especially in the spiral arms where star formation is ongoing. Population II stars are old, metal-poor, and found in the halo and bulge, having formed early in the galaxy's history. There is also an intermediate population, sometimes called the thick disk, which is older and more metal-poor than the thin disk, but younger and more metal-rich than the halo. The distribution of these populations within the galaxy depends on the galaxy's formation history. The thin disk, where most population I stars reside, is thought to have formed gradually over billions of years through the accretion of gas and the formation of stars. The thick disk and halo formed earlier, possibly through mergers with smaller galaxies or through the rapid collapse of gas in the early universe. By studying the spatial distribution, ages, and chemical compositions of stars in these populations, astronomers can reconstruct the timeline of the galaxy's formation. If the Milky Way's disk is more compact, the density of stars at a given distance from the Sun might be higher in the outer regions than previously estimated. Though this depends on the exact shape of the density profile, this could affect estimates of the star formation history, the rate at which stars have been forming over time. A more compact disk might indicate that star formation has been concentrated toward the inner regions, or that the outer disk has lost stars or gas through interactions with the halo or satellites. The metallicity gradient, the way that the abundance of heavy elements changes with distance from the galactic center, is another important diagnostic. In the Milky Way, metallicity decreases with increasing distance from the center, reflecting the history of star formation and chemical enrichment. Stars in the inner disk have higher metallicity because they formed from gas enriched by many generations of previous stars, while stars in the outer disk have lower metallicity because they formed from less enriched gas. If the disk is more compact, the metallicity gradient might be steeper, or it might extend over a smaller range of radii, unanswered questions and future directions. Despite the progress made in measuring the Milky Way and revising our understanding of its size and mass, many questions remain. These open questions will drive future research and shape the next generation of discoveries. Let's explore some of the key areas where our knowledge is still incomplete. One major question is the exact shape of the dark matter halo. While we know that dark matter dominates the mass of the galaxy and extends far beyond the visible stars, the detailed distribution is uncertain. Is the halo spherical, or is it flattened or elongated? Are there substructures, like clumps or streams of dark matter, left over from the accretion of smaller halos? The answers to these questions depend on the properties of dark matter itself, which remain unknown. Future observations of stellar streams and satellite galaxies will provide better constraints on the halo's shape and structure. Another question concerns the Milky Way's merger history. How many significant mergers has the galaxy experienced, and when did they occur? Recent studies using Gaia data have identified several major accretion events, including the Gaia-Enceladus merger about 10 billion years ago, which brought in a large amount of stars and gas. But there may be other, yet undetected events, especially in the early history of the galaxy. Understanding the full merger history is important for understanding how the galaxy assembled and how its structure evolved. The formation of the galactic bulge is another active area of research. The bulge contains a mix of old and young stars, and its structure is complex, with a bar-like component and possibly distinct populations with different origins. Was the bulge formed through the early rapid collapse of gas, through the buckling of the inner disk, or through the merging of smaller galaxies? Observations of the kinematics and chemistry of bulge stars, along with simulations, are helping to answer this question, but the full picture is not yet clear. The spiral arms of the Milky Way are also not fully understood. What maintains the spiral structure, and how long-lived are the arms? Some models propose that spiral arms are density waves, patterns that rotate through the disk, compressing gas and triggering star formation. Others suggest that the arms are material features, collections of stars and gas that move together. Observations of the ages and motions of stars in the spiral arms are helping to distinguish between these possibilities. The humbling lesson: why getting smaller makes us wiser. There's something deeply human about our tendency to overestimate our own importance, and this tendency extends even to our galaxy. For decades, we assumed the Milky Way was one of the giants of the local group, nearly equal to Andromeda in size and mass. We saw ourselves as cosmic heavyweights, one of the dominant structures in our corner of the universe. The discovery that we're actually significantly smaller, more of a middleweight than a heavyweight, is humbling in the best possible way. It reminds us that even our most carefully constructed models of reality are provisional, subject to revision when better data becomes available. The history of astronomy is, in many ways, a history of humiliation. Copernicus showed that Earth isn't the center of the solar system. Hubble showed that the Milky Way isn't the only galaxy, and that the universe is vastly larger than anyone had imagined. Later discoveries revealed that normal matter, the atoms and molecules that make up stars, planets, and people, comprises only about 5% of the universe's total mass energy content. Dark matter and dark energy, substances we don't understand and can't directly detect, dominate the cosmos. Each discovery has made us smaller, less central, less special. But there's another way to look at it. Each of these discoveries has also expanded our understanding, pushed back the boundaries of knowledge, and revealed a universe more magnificent and surprising than we had dared to imagine. Yes, we're smaller than we thought, but we're also part of something incomprehensibly vast and complex. The Milky Way might be the junior partner in the local group, but it's still a majestic spiral galaxy containing hundreds of billions of stars, many with their own planetary systems, some possibly harboring life. Being smaller doesn't make us less interesting or less worthy of study, it just makes us more accurate. The discovery also highlights the importance of constantly questioning our assumptions. For years, astronomers took it for granted that the Milky Way was massive because earlier studies had said so, and those studies were based on the best data available at the time. But science isn't about accepting authority. It's about testing and retesting our ideas against new evidence. Gaia provided that new evidence, and it forced us to revise our understanding. This is exactly how science is supposed to work, and it's a powerful reminder that what we know today might be overturned tomorrow by better observations. There's also a practical lesson here about the challenges of measuring things from the inside. Imagine trying to determine the size and shape of a forest while standing in the middle of it. You can see the trees around you, but your view of the forest's boundaries is obscured. You have to infer the forest's extent from indirect clues, the distribution of trees you can see, the sounds you hear from distant parts of the forest, the way the light filters through the canopy. That's essentially what astronomers face when trying to measure the Milky Way. We're embedded in the galaxy's disk, surrounded by stars and dust that block our view in many directions, forced to piece together the big picture from limited, incomplete data. What makes the recent breakthrough so significant is that we've finally developed tools, like Gaia, that can overcome these observational challenges. We can now measure the positions and velocities of stars across the entire galaxy with enough precision to map its structure in 3 dimensions. We can track satellite galaxies and use them as probes of the Milky Way's gravitational field. We can combine data from multiple sources, optical telescopes, radio telescopes, X-ray satellites, to build a comprehensive picture that's greater than the sum of its parts. Getting the Milky Way's size right is a triumph of observational astronomy and data analysis. Looking forward, the work is far from finished. The new mass estimate of approximately 1 trillion solar masses is the best we have, but it still comes with uncertainties of 10 to 20%. Future observations, from Gaia's continued operation, from new missions like the Nancy Grace Roman Space Telescope, from improved theoretical models of galaxy evolution, will refine this number further. We'll get closer and closer to the true value, though we may never know it exactly, but that's okay. Science is a process, not a destination, and the journey of discovery is what makes it worthwhile. In the meantime, The next time you look up at the Milky Way stretching across a dark sky, remember that you're seeing your cosmic home from the inside. Those thousands of stars visible to your naked eye are just the tiniest fraction of the galaxy's total population, the nearby neighbours in our little corner of the Milky Way. The vast majority of the galaxy's 200 to 400 billion stars are too distant and too faint to see without a telescope. And all of it, every star, every planet, every cloud of gas and dust, is held together by gravity in a structure that's smaller than we thought, but no less magnificent. We might be the little brother in the local group, but we're still home. And home is worth understanding, even when, especially when, the truth is different from what we expected. The Milky Way has revealed its true size to us, and in doing so, it's taught us humility, patience, and the importance of never assuming we have all the answers. That's a lesson worth learning, and it's one that resonates far beyond astronomy. In a universe full of mysteries, being smaller than we thought isn't a disappointment. It's an invitation to keep exploring, keep questioning, and keep discovering. Before you go, drop a comment below with your thoughts. Did you know the Milky Way was smaller than scientists thought? What surprised you most about this discovery? And if you enjoyed diving deep into the science of our galaxy, make sure to subscribe, hit that like button, and turn on notifications so you don't miss our next cosmic revelation. The universe is full of surprises, and we're just getting started. Keep looking up.